You have experienced the Bohr Effect without knowing its name. Every time you breathed too fast during a stressful moment and felt lightheaded, that was the Bohr Effect working against you. Every time you hyperventilated and felt tingling in your fingers, tunnel vision, a sense of unreality, that was your blood refusing to release the oxygen it was carrying. Not because the oxygen was gone, because you had blown off the molecule that tells hemoglobin to let go of it. Most people have experienced it more subtly, the vague fog after a period of shallow, rapid breathing, the dizziness that arises when you stand up after sitting anxiously, the breathlessness at rest that seems disproportionate to your fitness. These may have been attributed to age, to deconditioning, to cardiac or pulmonary causes. Some of them may be the Bohr Effect. Your blood carrying a full load of oxygen but releasing too little of it because the CO2 that governs the release has been depleted by a breathing pattern slightly faster than your metabolism requires. Molecule is carbon dioxide. You were taught it was waste. It is not waste. It is the delivery instruction, the signal that forces your blood to release oxygen to your tissues. And the physics of how that signal works means that holding your breath for 30 seconds can deliver more oxygen to your brain than a minute of deep breathing. If you have cardiovascular conditions or take heart rate lowering medication, approach breath holds conservatively. Start with 10 seconds and gauge the response before extending. The hemodynamic changes are mild but present, and they stack on existing cardiac medication the way the dive reflex does. That lightheadedness during stress, start there. Because the explanation for why breathing harder makes you feel worse is the key to understanding why breathing less can make you feel better. When a person breathes rapidly, whether from anxiety, from habit, or from the well-meaning instruction to take deep breaths during stress, arterial CO2 drops below its normal range of 35 to 45 millimeters of mercury. This is hypocapnia. CO2 is not merely being exhaled, it is being depleted, blown off faster than the cells can produce it, dropping below the concentration the blood needs to function. Two things happen simultaneously when CO2 drops. First, the cerebral arteries constrict. CO2 is a potent vasodilator in cerebral arteries. It directly relaxes the smooth muscle in the vessel wall, maintaining adequate blood flow to the brain. When CO2 drops, the arteries tighten, approximately 2% per millimeter of mercury of CO2 reduction. A person hyperventilating to a CO2 of 20 millimeters of mercury, typical during a panic attack, has constricted their cerebral arteries by approximately 30 to 50% compared to normal. Less blood reaches the brain. Second, the blood that does reach the brain delivers less oxygen. This is where the physics becomes counterintuitive and where the explanation requires a protein, a curve, and a discovery made in 1904. Hemoglobin is a tetrameric protein in your red blood cells. 4 subunits, each containing a heme group with a central iron atom that reversibly binds one molecule of oxygen. Each red blood cell contains approximately 270 million hemoglobin molecules. Each molecule carries 4 oxygen molecules. Blood leaving your lungs is approximately 98% saturated, nearly every binding site occupied. The oxygen is loaded. The carrier is full, but loaded is not delivered. This is the distinction that changes everything about how you understand your own breathing. Hemoglobin must release its oxygen at the tissues, unloading in the capillary beds of your muscles, your organs, your brain. The oxygen does you no good locked to hemoglobin. It must be released at the capillary level, diffuse across the capillary wall, enter the interstitial fluid, and reach the mitochondria inside your cells. Only then is it used. Hemoglobin that carries oxygen past the tissues without releasing it returns that oxygen to the lungs. A full round trip, loaded the entire time, delivering nothing. Binding between hemoglobin and oxygen is cooperative. Each oxygen molecule that binds increases the affinity of the remaining sites, making it easier for the next to attach, and each molecule that leaves decreases the affinity of the remaining sites, making it easier for the next to release. The relationship is sigmoidal, an S-shaped curve that describes how hemoglobin's grip on oxygen changes with the partial pressure of oxygen in the surrounding blood. This curve, the oxygen-hemoglobin dissociation curve, governs oxygen delivery in every vertebrate that has ever lived. Its position determines how much oxygen reaches your tissues versus how much stays locked to hemoglobin. The curve shifts left. Hemoglobin grips tighter, releases less. The curve shifts right. Hemoglobin releases more readily, delivers more. You cannot feel the shift. You can feel the consequences. Clarity, when delivery is efficient. Fog, when it is not. Right now, as you listen to this, the position of your dissociation curve is determining how much of the oxygen your lungs just collected is reaching your brain. If your CO2 is in the optimal range, 35 to 45 millimeters of mercury, the curve is positioned correctly, and hemoglobin is releasing oxygen efficiently at the capillary level. If your CO2 is below that range, from breathing slightly faster than your metabolism requires, from mouth breathing, from the shallow rapid breathing that chronic low-grade anxiety produces, the curve is shifted left, and your brain is receiving less oxygen than the blood is carrying. Your pulse oximeter reads 98%. Your cells are receiving less than 98% would suggest. The measurement captures loading. It does not capture delivery. The gap between loading and delivery is the dissociation curve, and the position of the curve is determined by CO2. In 1904, Christian Bohr, the Danish physiologist, father of physicist Niels Bohr, discovered the molecule that shifts this curve. Increasing CO2 concentration in the blood shifts the dissociation curve to the right. Higher CO2 means hemoglobin releases oxygen more readily. This is the Bohr effect. Mechanism is molecular. CO2 diffuses into the red blood cell. Inside the cell, the enzyme carbonic anhydrase catalyzes the reaction of CO2 with water, forming carbonic acid. Carbonic acid dissociates immediately into bicarbonate and a hydrogen ion. The hydrogen ion binds to hemoglobin, physically altering the protein's three-dimensional shape, reducing its affinity for oxygen. The oxygen is released. Tissue receives it. The entire sequence, CO2 entering the red cell, carbonic anhydrase converting it, hydrogen ion binding hemoglobin, oxygen releasing, occurs in the fraction of a second that the red blood cell spends transiting the capillary bed. The chemistry is fast enough to match the transit time. By the time the red blood cell exits the capillary, the oxygen has been released and the hemoglobin has changed shape. The delivery is complete before the blood reaches the venous side. This is happening in your body right now, at every capillary bed, in every organ, with every red blood cell that passes through. The CO2 your tissues produce is forcing the oxygen release that keeps those tissues alive. The system has been running without interruption since the moment you were born. The Bohr effect is not an occasional mechanism. It is the continuous operating principle of oxygen delivery in your body. Elegance is in the self-regulation. Tissues producing the most CO2, the most metabolically active, the ones consuming the most energy, automatically receive the most oxygen. A working muscle produces CO2 as a byproduct of oxidative metabolism. That CO2 enters the capillary blood, shifts the dissociation curve right locally, and forces hemoglobin passing through that capillary to release more oxygen precisely where the demand is highest. The tissue that needs oxygen most produces the signal that delivers it. The waste is the signal. Remove the waste, and you remove the delivery instruction. Think about what that means for your brain. Your brain, which consumes 20% of your total oxygen despite being 2% of your body weight, uses this system continuously. When you concentrate, when you solve a problem, when you engage in focused thought, neural metabolic rate increases in the active regions. Local CO2 rises. The Bohr effect shifts the curve right in those specific cerebral capillary beds, and hemoglobin releases more oxygen to the neurons doing the work. The system self-regulates at the level of individual capillary beds. No central dispatch, no conscious request. The brain does not ask for more oxygen. It produces CO2 as a byproduct of working, and the CO2 automatically increases oxygen delivery to the tissue that produced it. Person hyperventilating has blown off CO2 below the optimal range. The dissociation curve has shifted left. Hemoglobin's affinity for oxygen has increased. It is gripping its oxygen load more tightly. The blood is fully saturated. 98%, same as always, but the hemoglobin will not let go. The tissues receive less oxygen despite the blood carrying its full load. Simultaneously, the cerebral arteries have constricted from the low CO2. Less blood reaches the brain, and each unit that arrives delivers less oxygen. Result: cerebral hypoxia from too much breathing. The lightheadedness, the tingling, the tunnel vision, the sense of unreality, all produced by breathing harder, not by breathing too little. The person breathes faster because they feel they are suffocating. Every additional breath makes the oxygen delivery worse. The paradox is complete, and it is the Bohr effect running in reverse. If you recognize those sensations from your own experience, if you have felt that lightheadedness during stress, that tingling after rapid breathing, that fog that arrived precisely when you needed clarity most, you are experiencing two mechanisms operating simultaneously against you. Cerebral vasoconstriction, reducing blood flow. Left shifted dissociation curve, reducing oxygen release from the blood that did arrive. Both driven by one cause, CO2 blown off by rapid breathing. Both reversible by one intervention, allowing CO2 to rise back to its normal range. This is why the paper bag works. The person rebreathes their own exhaled CO2. Arterial CO2 rises back toward normal. Cerebral arteries dilate. The dissociation curve shifts right. Hemoglobin releases its oxygen. Symptoms resolve within 30 to 60 seconds, not because oxygen was supplied, but because the CO2 needed for oxygen release was restored. The oxygen was there throughout. The delivery instruction was missing. That paradox, breathing harder, producing less oxygen delivery, the intuition that more breathing means more oxygen being exactly backwards, is the inversion I cannot unsee in the respiratory literature, because it inverts the relationship most people assume between breathing and oxygenation. More breathing does not mean more oxygen delivery. It means less CO2, which means tighter hemoglobin binding, which means less release at the tissues. The correction for feeling breathless is not faster breathing. It may be slower breathing, or a brief pause. A distinction matters here because the common stress advice is not uniformly wrong. It is imprecise in a way that causes harm. The problem is not depth of breathing. It is speed. Slow, deep breathing at a reduced rate, 4 to 6 breaths per minute, does not produce hypocapnia. The slow rate reduces total ventilation, maintaining or even increasing CO2. Fast, deep breathing expels CO2 because the rate of ventilation exceeds the rate of CO2 production. The advice that causes harm is not breathe deeply. It is breathe deeply and quickly, which is what most people do when told to take deep breaths during stress. They increase both depth and rate. The rate is what depletes the CO2. The advice should be breathe slowly, and the Bohr effect explains why. Consider what this means for the person over 65 who has been told to take deep breaths during medical procedures, during anxiety, during episodes of chest tightness. If they responded by breathing both deeply and quickly, which is the natural interpretation, they may have been producing the cerebral hypoxia they were trying to prevent. The dizziness during the stressful medical appointment, the lightheadedness in the waiting room, the foggy thinking during a difficult conversation. Some of this may have been positional, cardiac, or medication related. Some of it may have been the Bohr effect, CO2 depleted by stress breathing, the curve shifted left, oxygen locked to hemoglobin, while the brain received less. Well, reverse the direction. If blowing off CO2 shifts the curve left and reduces delivery, the physics predicts that allowing CO2 to rise should shift it right and enhance delivery. A 30-second breath hold tests this, and the chemistry confirms it. A voluntary breath hold of 30 seconds produces a defined set of chemical changes. Your cells do not stop metabolizing because your lungs have stopped ventilating. Oxidative metabolism continues at its normal rate, consuming oxygen and producing CO2 with every mitochondrial cycle. Your lungs have paused. Your mitochondria have not. The CO2 that would normally be exhaled is accumulating in your blood. and the accumulation is precisely the shift the dissociation curve needs. Arterial CO2 rises from approximately 40 millimeters of mercury by roughly 3 to 5 millimeters of mercury over 30 seconds. This increase shifts the dissociation curve right. Hemoglobin releases oxygen more readily. Arterial oxygen saturation drops slightly, from approximately 98 to approximately 94 to 96%, because no new oxygen is entering the lungs. Drop in saturation from 98 to 95% sounds alarming if you think of saturation as a measure of oxygen adequacy. It is not. 95% means 5% of binding sites have released their oxygen, but the Bohr effect means the remaining 95% is releasing oxygen more readily at the tissues. Because the CO2 is higher, the curve has shifted right, and each hemoglobin molecule passing through a capillary bed releases a larger fraction of its load. Less oxygen in the blood, more oxygen reaching the cells. The arithmetic is counterintuitive, but the physiology is exact. Rising CO2 simultaneously dilates cerebral arteries, approximately 2 to 4% per millimeter of mercury of CO2 increase. More blood reaches the brain. Each unit of blood delivers more oxygen because the Bohr effect is now working in the correct direction. The warmth in the face at the end of the hold is cerebral vasodilation, more blood flowing through the facial and cranial vessels. The clarity is enhanced, oxygen unloading at the neuronal level. The sharpening is your prefrontal cortex receiving more oxygen than it was getting during normal breathing. You can test this right now if you have no cardiovascular conditions and are not on heart rate lowering medication. Exhale normally, close your mouth, and wait for 30 seconds. Do not take a deep breath first. Begin at the resting point of your respiratory cycle. Notice what happens when you resume breathing. The clarity, the warmth, the sense that something shifted. That is not placebo. That is the Bohr effect and cerebral vasodilation operating in real time. The dissociation curve shifting right, the cerebral arteries dilating, the oxygen delivery reorganizing in response to a 3 to 5 millimeter of mercury rise in CO2 that 30 seconds of not breathing produced. Your brain just received more oxygen than it was getting before the hold. The hold did not deprive it. It reorganized the delivery. You see, Chagate's research adds a third mechanism, even a dry breath hold. No water contact, no facial emotion, produces measurable splenic contraction after approximately 20 to 30 seconds. The spleen releases its reserve of concentrated red blood cells, increasing hematocrit by approximately 2 to 3%. Blood's oxygen carrying capacity rises within seconds. 3 independent pathways to enhanced oxygen delivery: Bohr effect, shifting the dissociation curve for enhanced release; cerebral vasodilation, increasing blood flow to the brain; and splenic contraction, increasing the blood's oxygen carrying capacity. From one trigger, rising CO2. The convergence is not coincidental. It reflects a body that evolved to use CO2 fluctuations as the master signal for optimizing oxygen delivery across multiple systems simultaneously. Think about what the acute effect tells you about the chronic possibility. Acute effect of a single hold is temporary. The CO2 rises, the curve shifts, the delivery improves, the CO2 is exhaled, the curve returns to baseline. The chronic effect of repeated holds is not temporary, and the mechanism is the chemoreceptor threshold. Your body has a CO2 threshold, a concentration that the chemoreceptors in your brainstem and carotid bodies treat as normal. When CO2 rises above this threshold, they trigger the urge to breathe. The urge is not optional. It is a brainstem reflex that produces an increasingly powerful drive to inhale. But the threshold at which it fires is not fixed across individuals. It varies, and the variation determines everything about how you breathe and how much oxygen you deliver. A person with a low threshold breathes more frequently, maintaining lower baseline CO2, producing a chronic left shift of the dissociation curve. Less oxygen delivered per breath, all day, without awareness. A person with a high threshold tolerates more CO2, breathes less frequently, maintains a curve position further right. More oxygen delivered per breath, all day without awareness. Two people sit in one room, breathe one air supply, share equivalent lung capacity. One delivers oxygen efficiently, the other does not. The difference is the chemoreceptor calibration, an invisible variable that no standard medical test measures and that determines the resting position of the dissociation curve for every breath they take. Calibration is not fixed. Chronic overbreathing trains it downward. The chemoreceptors adapt to a lower CO2, treating it as normal, maintaining a breathing rate that keeps CO2 below optimal indefinitely. Deliberate breath hold practice trains it upward, exposing the chemoreceptors to slightly higher CO2 repeatedly, nudging the threshold toward the level. The Bohr effect works best at. Principle was developed into a clinical method in the 1950s by Konstantin Buteyko, graduated breath holds and reduced breathing volume training, CO2 tolerance upward. Controlled trials showed reductions in bronchodilator use among asthma patients of up to 90%. Though the trials were small, blinding a breathing intervention is inherently difficult, and the result has not been replicated at the scale the magnitude deserves. The direction, reduced medication need with improved CO2 tolerance, was consistent across studies. Mechanism is CO2 restoration. Higher baseline CO2 produces bronchodilation through CO2's direct relaxant effect on airway smooth muscle, reducing the bronchospasm the medication was treating. The airway problem was, in a meaningful sense, a breathing pattern problem. Asthma result matters beyond asthma because it demonstrates that the chemoreceptor setpoint is clinically consequential, not a theoretical variable, but a measurable parameter that, when shifted, produces a 90% reduction in medication use in the most favorable trials. The bronchodilator was compensating for a CO2 level that was too low to maintain bronchial relaxation. When the CO2 level was restored through breathing retraining, the bronchodilator became largely unnecessary. The medication was treating a symptom. The breathing pattern was the upstream cause. The Bohr effect was the mechanism connecting the two. Buteyko's metric for CO2 tolerance, the controlled pause, is measured by exhaling normally, closing the mouth, and timing the interval until the first definite urge to breathe. Not the first mild sensation, the first genuine desire to inhale. Control, pause, is a Buteyko-specific metric, not a standard clinical measurement. But the CO2 tolerance it indexes is the physiological parameter. The Bohr effect predicts matters. A healthy control pause is 25 to 40 seconds. Many chronic overbreathers score 10 to 15 seconds. The gap between those numbers is the gap between a dissociation curve delivering oxygen efficiently and one holding it back. And here is what the chronic version of the paradox looks like, because the hyperventilation that produces acute symptoms has a quieter, subtler counterpart that many people live with daily without recognizing it. If you habitually breathe through your mouth, sigh frequently, take visible breaths at rest, or find your breathing audible to someone sitting beside you. Habitual overbreathing may be one contributor to symptoms you experience. These symptoms: cognitive fog, dizziness on standing, breathlessness at rest, fatigue that seems disproportionate to your activity level, have many causes in an adult over 65, cardiac, neurological, hematological, medication-related. Low CO2 from habitual overbreathing is one possible contributor that is rarely investigated. Not the explanation. A possible explanation, and one that is testable. Reason? It is rarely investigated is the pulse oximeter. Your doctor measures your oxygen saturation, sees 98%, and concludes the oxygenation is adequate. The number is reassuring. It is also incomplete. A pulse oximeter reads saturation. How much oxygen is loaded onto hemoglobin? It does not read delivery, how much oxygen-hemoglobin is releasing at the tissues. A person with 98% saturation and a CO2 of 30 millimeters of mercury is carrying a full load, but delivering less of it than a person with 96% saturation and a CO2 of 42. The second person has less oxygen in the blood, but delivers more to the tissues because their CO2 is forcing the release. The pulse oximeter shows them as less oxygenated. The Bohr effect shows them as better oxygenated at the cellular level. The measurement and the reality diverge because the measurement captures loading, not delivery. The gap between loading and delivery is the dissociation curve, and the position of the curve is determined by CO2 that no standard clinical visit measures. Clinical protocols for CO2 tolerance training in older adults typically begin with holds of 10 to 15 seconds, sufficient to begin recalibrating the chemoreceptor threshold without producing the hemodynamic fluctuations that longer holds generate. Progressive extension of 1 to 2 seconds per week is consistently reported in the literature. Over months, the threshold shifts. Baseline breathing slows. Baseline CO2 rises. The dissociation curve shifts right at every breath without conscious effort. Consider what the recalibration feels like in the first weeks. It is not a dramatic change in breath hold duration. It is a subtle change in breathing pattern, the kind of change you notice only because you are paying attention. Breaths become slightly less frequent. Pauses between breaths lengthen naturally, not forced, not conscious, simply the chemoreceptors accepting a slightly higher CO2 before triggering the urge to inhale. Volume of each breath may decrease. Less air moved per cycle, but each cycle more efficient because the CO2 level is higher and the curve is shifting right. You breathe less and receive more. The paradox that seemed impossible at the beginning of this discussion, less breathing delivering more oxygen, becomes the daily experience of a body whose chemoreceptors have been nudged toward their designed operating range. The paradox resolves not because the physics changed, but because your understanding of the physics changed. CO2 is the delivery instruction. More CO2 means more delivery. Less breathing means more CO2. Less breathing means more delivery. The logic is airtight once you accept that carbon dioxide is not waste. It is the signal. Over weeks, the control pause extends. The breathing rate slows. The baseline CO2 rises. And the dissociation curve, the curve that governs oxygen delivery at every capillary bed in your body, shifts right by a fraction that produces measurable improvement in oxygen delivery at every breath you take for the rest of the day. The recalibration is not a technique you perform. It is a threshold you shift. And once shifted, it operates automatically, below awareness, at every breath. That recalibration, the chemoreceptor threshold shifting upward through graduated breath holds, producing a permanent right shift of the dissociation curve that delivers more oxygen at every breath without conscious effort, is the fact I keep returning to in the respiratory physiology literature. Because it means the fatigue, the fog, the vague breathlessness that many people attribute to age may be partly a dissociation curve problem, not a lung problem, not a heart problem, not an oxygen problem, a CO2 problem. A body that has been breathing slightly too much for slightly too long, holding its baseline CO2 slightly too low, and delivering slightly less oxygen at every breath as a result. Christian Bohr discovered in 1904 that the molecule every textbook calls waste is the molecule that tells blood to deliver oxygen. 120 years later, most people still believe that breathing more means getting more oxygen. The physics says the opposite. The dissociation curve, the single equation governing oxygen delivery in every vertebrate, shifts right with CO2 and left without it. More breathing expels CO2 and shifts the curve left. Less breathing preserves CO2 and shifts it right. The molecule you were taught to eliminate is the molecule your tissues need in order to receive the oxygen your lungs collected. The dissociation curve is not a detail of respiratory physiology. It is the central mechanism of oxygen delivery in every vertebrate that has ever lived. Shift it left with too little CO2 and the blood holds its oxygen like a closed fist. Shift it right with adequate CO2 and the blood opens. You experienced the Bohr effect at the start of this discussion, the lightheadedness memory, the tingling. You have experienced it every day of your life without knowing its name. The curve has been shifting with every breath you have taken, governing oxygen delivery at every capillary bed, responding to the CO2 your cells produce and the CO2 your lungs expel. The question the Bohr effect leaves is whether the curve, right now, is sitting where it should, or whether it has been sitting too far to the left, in a body that forgot how to let its blood breathe.